Modern aircraft braking systems, which incorporate anti-skid units and other sophisticated devices, are extremely efficient. However, bad runway conditions can reduce the ability of even the most refined braking systems to the point where they become a liability. The addition of a reverse thrust capability has improved the situation so much that landing a modern aircraft on a wet and or icy runway in crosswind conditions need now hold no terrors for the capable pilot. This diagram compares the stopping distances involved when an aircraft lands on a wet and icy runway with and without using thrust reversal. The usual method of operating the reverse thrust system is to select it immediately the weight of the aircraft is firmly on the main wheels. This method of operation, coupled with the use of spoilers, can reduce the landing distance dramatically without producing friction at the wheel brakes. There are three basic thrust reversal systems presently in use. They are clamshell doors, bucket doors, external doors, blocker doors. All of these types of thrust reversal system are typically operated by hydraulic or pneumatic actuators or motors driving screw shafts. The reversing systems reverse the direction of the gas flow, thereby reversing the thrust. The name clamshell has been applied to this system of reverse thrust because of the shape of the reverser doors, which resembles that of a clamshell. In the clamshell door system, the reverser doors are usually pneumatically operated. They use high-pressure compressor air as the power source. Pneumatic rams move the reverser doors from their stowed forward thrust position to their deployed reverse thrust position. In their stowed position, the clamshell doors cover cascade vanes, which are revealed when the doors move to the deployed state. While they are deployed, the clamshell doors shut off the normal exhaust gas exit, forcing the gas to escape through the cascade vanes in a forward direction, so that the forward motion of the aircraft is opposed by the reverse thrust thus generated. The lower cascade vanes are aiming the exhaust mainly in a forward direction, but they are angled so that the exhaust has an outboard angular component as well. This outboard angular component minimizes the chances of debris and hot gases being re-ingested into the engine intake during the use of reverse thrust. The bucket reverser system is normally hydraulically operated. The rear portion of the engine exhaust pipe is shaped like two halves of a bottomless bucket, which are hinged to enable them to swing rearwards when selected, to deflect the exhaust gas forward. The cold stream reverser, or blocker system, is only used on high bypass ratio fanjet engines. The essential difference between the blocker system and both the clamshell door and bucket reversing systems is that while the latter use the hot exhaust as the means of reverse thrust, the blocker system, as its name suggests, blocks and diverts the cold bypass airstream only. Operation of the blocker system is initiated, as are the other two systems, by movement of reverse thrust levers in the cockpit. Each engine with a reverse thrust capability has a reverse thrust lever. In the case of the blocker system, the speed and direction of an air motor is determined by operation of the reverse thrust lever. The output of the air motor drives flexible shafts, which open or close the blocker doors, which, by their movement, either expose or cover cascade vanes, which direct the bypass air where it's required. In order that the pilot may have information regarding the position of the reverser doors, some form of warning is fitted. The warning can be amber lights positioned somewhere on the forward instrument array within full view of the crew, or, as is shown here, captions which appear on the electronic centralized aircraft monitoring system. The warnings will be shown whenever the reverser doors are unlocked and away from their stowed forward thrust position. Like a great number of things which purport to be beneficial, the reverse thrust system can, if wrongly serviced or mishandled, become more of a curse than a blessing. Safeguards have to be built into the reverse thrust system which will protect the aircraft in case of a malfunction or incorrect handling. Other indications regarding the reverse thrust system may be provided: reverser deployed, reverser operating, etc. These indications will be dependent upon the aircraft type. There are 5 safeguards built into the selection of reverse thrust. They are: reverse thrust cannot be selected on an engine until the throttle lever of that engine is at idle. Reverse thrust cannot normally be activated on an aircraft until that aircraft is on the ground. This is achieved through the air-ground logic interlock system. Some Boeing aircraft utilize the radar altimeter to restrict reverse thrust operation to below 10 feet above ground level. Having said that, operation of the reverse thrust system is not recommended while airborne. With reverse thrust selected, engine power cannot be increased above idle power until the reverse thrust doors are in the deployed reverse thrust position. If, while forward thrust is selected, the reverser doors inadvertently move to the deployed reverse thrust position, the throttle will automatically close to idle. If, while reverse thrust is selected, the reverser doors inadvertently move to the stowed forward thrust position, the reverse thrust lever will automatically go to the reverser deploy position. While there is normally no restriction on the upper speed at which reverse thrust can be selected, there are aircraft which have reverse thrust systems fitted that restrict the minimum speed of operation of the reverse thrust system. Earlier, it was described how the reverse thrust was angled forwards and outwards. This was to minimize the chances of debris and hot gases being re-ingested into the engine. There is, nevertheless, a clear danger that, despite the angle of the cascade vanes, if the aircraft is only moving forward slowly or is stationary, the depression in the engine air intake will overcome the impetus caused by the deflection applied to the exhaust gas stream and any associated debris and suck it into the compressor, with potentially catastrophic consequences for the engine. To prevent the likelihood of this happening, the standard operating procedure on some aircraft is to reduce the position of the reverse thrust lever to the reverse idle position at typically 60 to 80 knots. Subsequently, at a speed where it's considered there is no further benefit to be gained from maintaining that idle reverse position, that is, when it's judged that there is no further requirement for a sudden selection of full reverse power, usually at about 50 knots, the reverse thrust lever is returned to the stowed position. Reverse thrust is not normally to be used for ground maneuvering. When the reverse thrust system is in use, engine indications must be closely monitored, in particular the exhaust gas temperature. It should be borne in mind that re-ingestion of the exhaust gases will cause the EGT to increase, perhaps exacerbating a situation where high ambient temperatures are already causing the EGT to be close to its limit. Care must be exercised when increasing reverse RPM that the engines respond symmetrically, as adverse yaw can be induced if they are not. This could be particularly embarrassing when applying full reverse thrust when landing on a slippery runway. There may also be a performance limitation imposed if one engine thrust reverse system is inoperative, as the total reverse capability will be reduced, and on an aircraft with 2 pod-mounted engines, having one engine thrust reverse system inoperative may mean that the remaining serviceable reverser cannot be operated either, because of the asymmetric effect it would impart upon selection. This concludes the lesson on reverse thrust.